Hello folks, I am back after a long time. So it is because we have been busy in a textbook for our own board of the country. So a bit of sabbatical from A level, A level, and it was also because the recent patterns in the exams or the recent happenings in the exam schedules also disturb our interest in solving of questions, because people have been showing less interest in the studies and any academic activities. Maybe they are onto something else. That's why we also thought that our attention should focus to something meaningful for present and the future. That's why. So now I am back, and it will be a regular feature now because I have got some time. So I have got some extra time from that work. Now today I am doing paper 4. Paper 4. It is paper 4-2, February-March session 2020. The freshest question, and the question number is 9. It is concerned with the chapter alternating current. It says that the output of a power supply is represented as V equal to 9.0 sine 20t. So the equation should have been V equal to V naught sine omega t. So now it is so this thing has been the values according to the value, it is V equal to 9.0 sine 20t, where V is the potential difference in volts and t is the time in seconds. Determine for the output of the supply the root mean square voltage Vr.m.s. So Vr.m.s is simply equal to V naught by root 2. That's equal to 9.0 by root 2. So it will be equal to, if I do in the calculator, it will be 9 divided 2. So it is simply 6.3639. So I'll just write 6.36. 6.36 volt. It is 6.36 volt. The period t. So the time period is equal to 2 pi by omega, and according to the comparison, omega is 20 here, so it's equal to 2 pi by 20. That will be equal to, so it's 2 into pi divided 20 equal to, so it is 0.314 in 3SF. 0.314 and seconds. Now number B, the variations with time t of the output potential difference V from two different power supplies are shown in figure number 1 and number 2. So this is a sinusoidal wave and this is square wave. So sinusoidal wave means something that gives sounds like this, like this. The sound will be something like, and here the sound is something like something like buzzer sound, something like the sound of a tuning fork. So the graphs are drawn to the same scale, so the scaling is same. Then explain whether the same power to be dissipated in 1 ohm resistor connected to each power supply. So will they give the same power? It says no. It's because here the power is given by, in the first, the power is given by power is equal to Vr.m.s square by R. R is 1 ohm, so it's simply equal to magnitude of Vr.m.s square, that's equal to V naught by root 2 squared equal to V naught square by 2. Power here, power in case A. But in power case B, power B, it's equal to, the voltage is constant. So that's why it's equal to Vr.m.s square by R. That's equal to simply V naught square by R, and that's equal to V naught square by 1. So let's use 1 here, so it's equal to V naught square. So that's why the powers in the two cases is different. So that means the square wave can have more power at the same peak level, or at the same level that we see outside. The square wave will be giving more power, and that is the basic philosophy of digital circuits. So in digital we have got only high or low, so high, low, not in between, and that can deliver us more power out of the same source. The basic principle of digital circuit or logic is that, and later on lots of other factors got added, but the basic is that. Now next number, The power supply in A is connected to a transformer, of course. The input power to the transformer is 80 watts. So it is power in is equal to 80 watts. The secondary coil is connected to a resistor. The RMS voltage across the resistor is, so in the secondary it is, so Vr.m.s in the secondary is equal to 120 volt, and the RMS current r.m.s in the secondary is equal to 0.64 amperes. Calculate the efficiency of the transformer. So the efficiency is equal to power out by power in, and power out is equal to, the power is calculated in the form of RMS, so that's why it's equal to r.m.s secondary and Vr.m.s secondary divided by this 80, so it's equal to 0.64 into 120 divided by this 80, and that's equal to, let's do the calculations. So we'll have 0.64 into 120 divided 80 equal to, so it is 0.96. So it is 0.96. We can express it as percentage also, 96 percentage. So it is either 0.96 or 96 percentage. Any notation is okay. Now number 3, state one reason why the transformer is not 100% efficient. So it has got many reasons. So one of the reasons is the ohmic loss. Let us say ohmic loss across the wires, across the wires constituting the coil, constituting the coil. So one of them is ohmic loss across the wires constituting the loss, one of them. The next one could be that the flux lines from the primary, all of them are do not get linked to the secondary. That means most of them get wasted somewhere else. That could be one reason. The other could be the development of eddy currents. So in spite of lots of mechanisms done to reduce eddy currents, some are still there. The eddy currents are random currents that develop in the iron core itself. The core itself, that's why, which does not reach the secondary. And similarly, we have got hysteresis losses, because whenever we say magnetism, there is always hysteresis, which means that there's a delay in magnetizing and demagnetizing. And this magnetizing and demagnetizing is an essential part of alternating current, because sometimes current is zero, sometimes current is positive, sometimes negative. So there's a lot of magnetizing, demagnetizing, reverse magnetizing, and there's always a delay. So during this delay, there is power loss. So lots of reasons. So we have to state only one, and we stated the most simple one here. Okay, thank you.